Welcome back, everybody, and welcome to exercise 2 on page 67. This is another example of doing a triple integral that's similar to the one that we did in exercise 1. In fact, it's asking us the same type of a question here. It's giving us the density of a solid region in grams per centimeter cubed and asking us, first of all, about finding the mass of the solid region. Okay, in this case, they were nice enough to already give us a picture of our region. That should help us greatly in finding our limits of integration. So to get started in this, we know from the previous example that finding mass is about integrating the density. Okay, so I'm going to start there. And we're going to evaluate this integral by setting up an iterated integral with 3 integrals involved. That means that we need to choose a direction. Okay, and how about if we choose the same order of integration that we did in the previous example? So we'll take our density function, which we know is 6x, and we'll integrate in the dz, dy, dx order. Okay, it's up to us to figure out what the limits of integration are. Okay, so we'll draw some pictures to help us do that. And the first picture that I'd like to draw is just kind of a recopied version of the one that you see above here. Okay, I'll do my best to just redraw that picture. Okay, you can see that my drawing skills are not stellar, but I think that's good enough to get the idea here. All right, label some of those intercepts. Okay, and we're integrating in the z direction first. That innermost integral is going to go between surfaces. So we want to ask ourselves then, what would the lower and the upper surface be if we integrate top to bottom? Okay, we'll write those down here. Okay, well, that's like asking you, if you picked a point down here at the bottom of a region and just went straight up until you smacked into the top of it, what would the z be at the top and the bottom? Okay, well, down here at the bottom, notice that we're in the xy plane, so z is going to be 0 there. The bottom of this region is flat. Z is always 0. And then what about at the top? Okay, what is the equation of the surface that's at the top of our region? Well, that's the plane 1 minus x in this case. So we've just found the lower and the upper surface. Okay, and we can go ahead and fill in that as our limits of integration in the z direction. Okay, we're now done with the z direction, so we're going to take that light and shine it down the z-axis. Let me just label our axes here. X, Y, and Z. So if we do that, we shine the light down the z-axis and think about the shadow that we're going to get in the xy plane. You can kind of see that what we're going to see as a shadow is this square down here. Let's redraw that square to the right. Okay, you can see that the size of that square is just going to be 1 by 1 in this case. And now we can talk about the y limits of integration, which would be asking what's the upper and the lower curve in this projection picture that we've drawn. Okay, well, let's see. If we go from bottom to top, we're dealing with just horizontal lines, just like we did in the last example. So on the top, we've got y equals 1, and on the bottom, we've got y equals 0. So those are our upper and our lower curves. And they tell us what our limits of integration on the middle integral are. We're going from 0 to 1. Okay, and then finally, we are now done with the y direction. So we're going to shine a light down the y-axis and ask, what's the shadow on the x-axis? Well, we're just going to get the shadow that's a line in this case, and you can see that that line goes from 0 to 1. Okay, and so 0 to 1 should be our limits in the x direction. Okay, good. So we've got the hard part out of the way, and down below we'll actually evaluate this integral that we just set up. Okay, so let's rewrite it. All right, and the first thing that we need to take the antiderivative of is 6x with respect to z. 6x is a constant, so when we take that antiderivative, we're just going to get 6xz. Okay, and that's going to be evaluated between z equals 1 minus x and z equals 0. Okay, let's go ahead and fill in our z values. Okay, so if we plug in z equals 1 minus x, we're going to get 6x times 1 minus x. If z is 0, we're just going to get 0, and so we're going to get that times dy dx. All right, so let's see, what's this going to look like? We're really integrating just 6x times 1 minus x now, dy dx. And what's interesting is when we do the next integral dy, there are no y's in that function. So it's like we're integrating a big constant. We're just going to get 6x times 1 minus x times y for that antiderivative. Okay, and y limits go from 1 to 0. Okay, so if we substitute in 1 and 0 for y, upper limit is going to give us just 6x times 1 minus x. And the lower limit's going to be 0. This seems to be happening over and over again. And we're integrating with respect to x. Okay, so finally, we've managed to reduce this down just to an ordinary calculus 1 integral. Okay, antiderivative for that is going to be, well, let's first distribute it out. So if we take 6x and multiply it through, we're going to get 6x minus 6x squared. Okay, and then quick antiderivative for that would be 3x squared minus 2x cubed. Evaluate between 1 and 0, and we're going to get an answer of 1. And our unit should be grams in this case. Okay, does that make sense for the units? Let's check. Okay, so our density was in grams per centimeters cubed, and distances are measured in centimeters. So if you multiply those units, you're going to get grams. Okay, there's just a quick confirmation that our units are correct. Okay, and we're done with part A. What about part B? Well, part B is similar to the part B that we did in the previous. So they say without calculating an integral, explain what the integral of e dv represents. Okay, well, let's think about that. If we do that integral, we are just adding up little cubes of volume, and volume has units of centimeters cubed in this problem. So what we're doing is we're just kind of going over our entire region E, and we're adding up cubes of volume, and so this must just give us the volume of E. Okay, just like part B in the previous exercise.